a la segunda parte de el programa del día de hoy, del simposio llamado Lo mejor de las ciencias de la Universidad de California en Los Ángeles, o UCLA en México. Mi nombre es Miguel García Garibay, soy profesor de la Universidad de California y soy uno de los coorganizadores de este simposio con el doctor Eusebio Juaristi, que es realmente el huésped de la ocasión el día de hoy. Luego de una mañana muy interesante, escuchando varias pláticas, tenemos ahora un programa que incluye 2 pláticas que son extremadamente interesantes por 2 de mis colegas en la universidad. La primera presentación va a ser por la profesora Jean Turner, que es profesora y directora del Departamento de Física y Astronomía. Jean es una científica americana muy notable, con una trayectoria muy interesante. Ella comenzó su educación en la Universidad de Harvard, donde obtuvo su grado de licenciatura, Arts Bachelor. Posteriormente se mudó del este de los Estados Unidos al oeste, a la Universidad de California en Berkeley, donde obtuvo primero su maestría y posteriormente su doctorado ahí mismo en la Universidad de California en Berkeley. Ella llegó a la Universidad de California en Los Ángeles en 1997, fue cuando comenzó su carrera. Después de un poquito antes en realidad. Hizo un postdoctorado en el Centro de Astrofísicas en el Harvard Smithsonian Center para Astrofísicas y luego comenzó su carrera independiente como profesor asistente en UCLA. Posteriormente fue consultante de TRW Incorporado. Después ascendió los rangos profesoriales de la Universidad de California, convirtiéndose en profesor asociado. Posteriormente fue la vicedirectora del Departamento de Astronomía. Posteriormente fue profesor visitante del Instituto Tecnológico de California, el Caltech. Ella tiene el título de Caroline Herschel Visitor del telescopio espacial del Space Telescope Science Institute y ha sido también científico visitante de la ALMA oficina en Santiago de Chile. Y desde 1997, ahora sí, ella ha sido profesora titular y profesora de la Universidad de California. El último rango que tenemos allá, que es profesora secas, me supongo. Jean tiene muchas colaboraciones con científicos, astrónomos mexicanos y chilenos, y le decía yo a Jean que la comunidad astrofísica y astronómica es una comunidad muy unida que tiene un impacto muy grande, creo, en todas las ciencias, y me da muchísimo gusto presentarles a ustedes a la doctora Jean Turner. Jean.
Gracias, Miguel. Buenas tardes. Es un honor y un placer estar aquí en el Colegio Nacional de México para darles una charla sobre el Departamento de Física y Astronomía de la Universidad de California, Los Ángeles, y también para describir mis investigaciones astronómicas. Mi español no está tan bueno, pero quizás está un poco más fácil para ustedes. El Departamento de Física y Astronomía, ante todo, quisiera presentarles el departamento. Actualmente yo soy jefa del departamento. Somos 59 profesores, 44 son físicos y 15 son astronómicos. Todos son activos en estudios, incluso a un profesor que tiene 101 años de edad. Still es activo. Amamos nuestro trabajo. Tenemos casi 600 estudiantes y 180 estudiantes postgraduados, y también hay muchos investigadores con doctorados. Es un departamento muy grande. Hay muchas áreas de investigación en el departamento. Eso es la lista de áreas. Ofrecemos grados en física y en astronomía y astrofísica. Algunos temas de investigación, no tiene tiempo por todo. Quizás nuestro grupo más famoso es lo de física del plasma. Tenemos un dispositivo gigante que produce plasmas. En inglés se llama el LAPD, el mismo nombre del policía de Los Ángeles. Ese instrumento plasma es utilizado por los científicos internacionales. También hay un grupo que estudió la física de átomos y moléculas, controlándoles precisamente con la luz del láser. Es posible estudiar muchos procesos físicos con sus instrumentos. Hay también especialistas en microscopía que pueden hacer imágenes de átomos individuales. Finalmente, hay un científico que produce luz de sonido, sonoluminescence. Soy astrónoma, eso es mi área. Astronomía y astrofísica de UCLA. El observatorio Keck es muy importante. Él consiste de 2 telescopios de 10 metros en diámetro. Son operados por la Universidad de California y Caltech. Ejemplos de investigaciones de la División de Astronomía y Astrofísica. Aquí son la láser de Keck. Son la láser de Keck que crean gotas de luz en el aire. Efectivamente, las estrellas artificiales. Estas estrellas artificiales están usados para afinar las imágenes, como lo de siguiente foto aquí. Esta foto muestra las órbitas de estrellas cercanas al agujero negro supermasivo de nuestra galaxia. Este agujero negro es 4 millones de veces más masivo que nuestro Sol. Las estrellas aquí, las órbitas, las estrellas son observadas desde hace 20 años. Las que son más cercanas al agujero negro se mueven más rápido, las órbitas aquí. Finalmente, el laboratorio infrarrojo, o IR Lab en inglés, se construyen instrumentos para detectar luz infrarrojo. Estas cámaras y espectrógrafos son para telescopios grandes como Keck y la próxima generación de telescopios como el telescopio de 30 metros o TMT. Y ahora voy a describir la ciencia que yo hago. Para mí, la ciencia es como un rompecabezas gigante. Se buscan las piezas y dónde meterlas. En esta charla les explico la mía pieza del rompecabezas. Por astrónomos, eso es el gran rompecabezas. Es la historia del universo en un dibujo. El universo comienza como gas y ahora es estrellas y galaxias. Es un proceso muy largo y complicado, pero para mí es más simple. Para mí, eso es la historia del universo, es la formación de estrellas de nubes de gas. Y eso es el proceso básico del universo. La fuerza principal es gravedad. Gravedad es una fuerza independiente de dirección, así que se trata de sacar las nubes en puntos o casi puntos. Por estrellas hay una fuerza opuesta de la gravedad, es la presión de calor, y estrellas como Sol tienen un equilibrio entre la gravedad y presión. Este equilibrio determina el diámetro de la estrella. Eso es muy bien entendido. Es demasiado simple. El proceso es más complicado. Pero, ¿qué tal un cúmulo estelar como este? Es un cúmulo globular. Hay unos millones de estrellas en este cúmulo y todos tienen la misma edad. Se forman al mismo tiempo. Eso no entendemos para nada. ¿Cómo se forman? La Vía Láctea tiene aproximadamente 200 de estos cúmulos y probablemente más en el pasado. Todos son muy antiguos, casi es antiguo como el universo. Sus formaciones es un gran misterio. Son la cuestión de millones de puntos de atracción al mismo tiempo, pero también el cúmulo se forma con muchas estrellas O. ¿Cuál es una estrella O? Estrellas O son poco común. Nuestro Sol no es una estrella O. Solo 1% de todas las estrellas son estrellas O. Son las estrellas más masivas, más poderosas y más luminosas de todas. Estrellas O son 1 millón de veces más poderosas que nuestro Sol. La mayoría de estrellas O se forman en cúmulos tan masivos como cúmulos globulares. La pregunta es, ¿cómo es posible formar cúmulos globulares con estrellas O? Eso es una estrella O de diferentes edades. Una sola estrella O puede ser extremadamente destructiva. Les explico los círculos luego. Estas estrellas son muy azules y emiten luz ultravioleta intensa. Esta luz calienta y ioniza el gas cercano, como la gran nebulosa de Orion, the Great Nebula of Orion, aquí arriba. Cuando envejecen, un poco más tarde, tienen vientos fuertes y pueden perder casi 80% de su peso así. Es como estrellas Wolf-Rayet, mucho más perder. Al fin, algunos pueden explotar como un supernova y a veces forman agujeros negros. Estrellas O se apagan rápidamente en solo 1 millón de años. Los círculos. Los círculos son del mismo tamaño que el núcleo de un cúmulo globular, como este tamaño. Un cúmulo globular puede tener 2000 estrellas O en este círculo. 2000. Imagínense lo que hacen estas estrellas a su misma, a su cúmulo, a su galaxia. Esas estrellas pueden explotar mientras el cúmulo se forman. ¿Cómo se forman así? Con so many estrellas O. Soy observadora y mi trabajo es obtener imágenes de cúmulos globulares todavía encajando en su nube de nacimiento. Las nubes contienen una mezcla de gas y polvo, como este. Las estrellas y gas no son visibles en luz ordinaria, como así es negro, sí, estrellas aquí, gas y polvo aquí. Es posible detectar la luz de gas y de polvo en la luz de longitudes de onda en el submilímetro. Eso es un diagrama del espectro electromagnético aquí, y en esa parte del espectro son de luz, de polvo y moléculas emiten aquí. Las observaciones en esta parte del espectro necesitan cielos secos y telescopios en montañas altas. Y el desierto de Atacama tiene ambos. Es muy seca allá. Esa foto es de una área cercana a la ciudad de Calama, en el norte de Chile, donde no ha habido lluvias desde hace un siglo. Es muy seco. El telescopio ALMA. Atacama Large Submillimeter Array es ALMA. ALMA es una colaboración internacional entre Norteamérica, Europa, Japón y Chile. Y Norteamérica consiste de USA, México, Canadá y Taiwán. Un poco raro. Y Chile consiste de Chile y China. Es una colaboración muy interesante. Esta foto es de ALMA en el principio de ciencia. Pueden ver los telescopios en esta foto aquí. Son 64 en todo, la mayoría de 12 metros en diámetro. ALMA está a 5,000 metros de altitud. Es muy alta. Hay una casa aquí que es el más alto en el mundo. Okay. Eso es mi galaxia. NGC 5253. Es una galaxia enano esferoidal. Tiene solo 1% de peso de la Vía Láctea y no tiene mucho gas. Pero hay estrellas y cúmulos masivos jóvenes. Entonces hay el nacimiento de estrellas. ¿Cómo ver el gas en el espacio interestelar? ¿Cómo detectar? No es fácil. La mayoría de gas en cúmulos suficientemente denso para formar estrellas es moléculas de hidrógeno, pero el gas hidrógeno no emitir la luz fácilmente en nubes frías con temperaturas de 10 Kelvin. Pero monóxido de carbono, o CO, es fácilmente excitado en estas nubes. Entonces, la luz de la línea espectral de CO es el mejor para buscando el gas que puede formar estrellas. Ok, ahora voy a mostrar algunas fotos de gas molecular, porque las ondas de longitud de submilímetro no son visibles a nuestros ojos. Voy a usar color falso. Color falso, por eso. La primera vista de CO en la galaxia NGC 5253. En rojo es CO y la luz visible from Hubble Space Telescope en azul. El CO es, la mayoría de CO es afuera de la galaxia. Ese punto aquí es interesante, pero no tiene mucho gas, es muy caliente, es muy brillante en CO. Por eso. Es muy raro tener gas afuera de la galaxia. Y eso es el mismo línea de esa foto es con el Submillimeter Array de Mauna Kea. Y eso es de ALMA. Es el mismo CO, pero es una foto mucho más fino. Y las nubes son muy pequeñas, solo 15 light years in size, muy pequeños, aproximadamente el tamaño de cúmulos globulares. Now, el mismo imagen CO, código con código de color por velocidad. Usando el shift Doppler, si las nubes que emiten CO se mueven hacia nosotros, se parece un poco más azul. Y si las nubes mueven más lejos de nosotros, parece un poco más rojo. En esa manera puede determinar velocidades a lo largo de línea de visión. Y ese filamento se mueve hacia la galaxia y más lejos de nosotros. Ese filamento está cayendo entre la galaxia. Creemos que ese es porque NGC 5253 pueden formar cúmulos globulares y no la Vía Láctea. La gravedad de la galaxia ayuda a la gravedad del cúmulo núcleo a acumular gas. Y dos más imágenes. Un close-up de la región centro es región. En el núcleo es un cúmulo globular en formación. So, esa región es ese. Esta foto es construyendo de imágenes de 3 telescopios, ALMA, Hubble y Keck. ALMA es en azul, las nubes que emiten CO, Hubble, estrellas y gas caliente y ionizada, luz visible es rojo, es Hubble, luz visible. Verde es polvo y luz de infrarrojo. Es polvo en infrarrojo. So, polvo aquí y polvo aquí. Aquí es el cúmulo que se forman. Más cerca, el cúmulo es aquí, es una región con no luz visible, es completely oscuro. El CO, nubes de CO aquí. Now I'm going to switch to English for a little while. I have some colleagues online, I think. This is a very new image of this system. This is a paper that we have submitted. This is one of the first views of carbon monoxide and dust in this galaxy, and we've been able to localize it with the Keck telescope very well to this. This cluster is very surprising because although it has 2,000 O-stars, it still has CO gas. The O-stars have not blown out the gas. Moreover, it has lots of dust. In fact, it has probably 10 to 15 times as much dust as we expected, and the O-stars within it probably created the dust. So for my colleagues online, this cloud has 3 times solar metallicity. So it's very enriched gas. So it can contain, in spite of those O-stars that are so destructive, it still maintains its gas. And the thing that we are learning in these observations is that the individual stars here look like isolated star-forming regions. And we think it could be because of the dust and the fact that dust isolates the individual star-forming regions. So this is how we figure out how a globular cluster could form, is by doing observations, and we see these things we didn't expect. Another thing we see is from the line profile, and this is another thing having to do with the Doppler shifts within. We can see that the CO emission, which is in blue and in contours, the line is very smooth, and it shows that there are many small clouds in there. So there are hundreds of little forming stars in there. And also, we see ionized gas emission, the same thing. It looks like isolated star-forming regions. So even though we are so far away from this galaxy, 15 million light years, we can still tell what is going on inside this forming globular cluster. Así que ese cúmulo se forman en la presencia de estrellas O con mucho gas y aún más polvo. Ahora necesito aprender cómo. Y esa es mi pieza de la rompecabezas. Y una pregunta más. ¿Es posible que ese cúmulo es el comienzo de formación de un agujero negro masivo? Es un gran misterio cómo se forman agujeros negros, como el de our Galactic Center, o los agujeros negros discovered in gravitational waves by LIGO, 30 veces más peso que lo del Sol. Es posible que se formen así. Es el comienzo. Eso es el fin. Desde el desierto de Atacama, trabajaba en Chile por 3 meses. Tomé esas fotos. Es un vicuña curioso. Gracias por su atención.
Muchas gracias, Jean, por esa presentación tan elegante. Si tenemos preguntas de la audiencia, la doctora Turner seguramente amablemente las responderá. Ya tenemos una pregunta atrás.
Hi, and thank you so much for your presentation. I don't know if you heard today about the Stephen Hawking's, they asked him about what was before the universe was formed. I couldn't read the note, but I don't know if you read about it. Like he made a statement of what was before the universe formed or something like that.
Before the universe. Okay, there are people who think, for a long time physicists said that's not physics. We can't really deal with that. We can go back to 10 to the minus 43 seconds, and that's as far as physics goes. Before that, we can't answer it. But there are many physicists now who don't like the current model. So if I go back, let's see, this, in particular, what bothers them. I'm getting close. This picture of the history of the universe, if I go back to this, is this era of inflation here. So there has to be an era, I'm not sure, yes, inflation, when the universe just sort of takes off and expands. And a lot of physicists say that doesn't work. And so now people are thinking it's a bouncing universe. So then that raises the question, when did the bouncing start? But they think there was a universe before and that there was a bounce. So that's the latest thinking. So you're right on top of it. They're still trying to figure out, it's not well accepted, but yes, that is the latest.
Otras preguntas, other questions? I have a question, Jean. So the CO emission, is that is an ion that is an excited state decaying, or is it a nuclear? What is the molecular event that releases that emission? Is it a...
The transition is rotational energy.
Rotational energy.
So it's a very, very low energy to appear at those wavelengths. And it also has to be excited in clouds that are only 10 degrees above zero. And so that's the problem with hydrogen. Hydrogen's the most abundant element. And this is why we struggle to look at gas. The universe is stars and it's gas. And I'm interested in starting out with the gas, but hydrogen has, to excite it, requires at least 500 degrees. And 500 degrees is very warm. 500 degrees Kelvin is very, very warm. Most of interstellar space is colder. And so to see it, we need something. And CO is good. It's bright. It's easily excited at 5 degrees Kelvin. And so this is why it's the first thing that we go to. But it's not the primary thing. And early in the universe, it was all hydrogen and helium, and no carbon and no oxygen. So in the, back in the history of the universe, all the gas was with hydrogen and helium, and so we couldn't see CO. So people studying the earliest galaxies in the universe have a real challenge, because we have to figure out how much CO there is. If we're trying to figure out how much gas, we have to know what the ratio of hydrogen to CO is, and that changes. And dust can be used too, but the ratio of dust to gas can change. And that's actually what we're seeing in this cluster. It's enhanced by at least an order of magnitude, 10 times over what we expected. And we think it's the stars putting it out. So it's a huge challenge. Mexico has another, I didn't mention it in the talk, has a telescope, the LMT, that also does submillimeter. The submillimeter band of the spectrum is perfect for observing CO and dust. And so we're going to be learning a lot about gas and dust in the universe in the coming years with ALMA and with the LMT from Mexico.
Thank you. ¿Alguna pregunta más? Yo tengo una pregunta más. El polvo, ¿cuál es la composición del polvo?
El polvo. Silicates and carbon. It depends, but it's a lot, I think, like olivine on Earth. We're not entirely sure. We do have a spectrum. It emits a spectrum, and so we can sort of tell what's in it. But silicates are a big part of it. And these stars produce, in the process of fusion in their centers, they produce magnesium, silicon, carbon, and put them out, and then dust has to form from those elements. So that's another thing we don't understand, is how dust could form. And we know the stars produce those elements, but then having the dust form is a different story, but we see it. So we know it's there.
No es muy diferente del polvo que tenemos aquí, entonces.
Sí.
Ok, gracias, Jean. Por favor, ¿por qué no se unen conmigo a agradecer a la doctora Turner por una presentación tan buena? Perfecto. Bueno, nuestra siguiente presentación es por el profesor Mark Hancock del Departamento de Estadística en UCLA. El profesor Hancock también es el director del departamento. Él inició su educación con un grado de licenciatura en honores en matemáticas en la Universidad de Western Australia. Después hizo su doctorado en estadística en la Universidad de Chicago. Y después hizo estudios postdoctorales en IBM, de Thomas Watson Research Center. Y después, por unos años, fue profesor en la Universidad de New York University, donde desde 1990 hasta 1996 escaló los rangos profesoriales, siendo profesor asistente, profesor asociado y luego profesor completo, full professor. Después se cambió a la Universidad de Pensilvania, a la que se conoce como Penn State, donde también fue profesor asociado de Estadística por un periodo de 1996 a 99. Y a Mark le gustaba moverse mucho porque después se movió a otra universidad y fue profesor de Estadística y Sociología en el Departamento de Estadística y Sociología en la Universidad de Washington. Y finalmente, en el año 2010, UCLA tuvo la fortuna de que decidió venir a Los Ángeles, donde ha sido profesor desde ese año, desde el 2010, y ha sido el director del departamento desde el año 2015. Ha tenido un gran número de honores, como por ejemplo recibió el premio Richard Lester lo voy a leer en inglés, por el Outstanding Book in Labor Economics and Industrial Relations. Después fue elegido Fellow de la Asociación de Estadística Americana. Y en el año 2012 fue el ganador del International Network for Social Network Analysis por el paper más citado en los 5 años anteriores, lo cual quiere decir que su trabajo ha tenido un impacto enorme. Me da mucho gusto presentarles a ustedes al profesor Mark Hancock. Mark.
Very nice introduction. It's actually of great joy to be here today, not only to meet and see each of you, but also to see the breadth of science that was presented in the earlier talks. And it's extremely interesting, and the young people here are extremely lucky to be able to be at the beginnings of their careers with all the exciting things going on in science. What I'm going to do is talk about an area of the physical sciences that doesn't have its own subject matter in the physical sciences. I'm going to speak here about the statistical sciences and also as a representative of the mathematical sciences here. So what do the statistical sciences do? And you can see from this description here where the science who takes as its subject matter how to learn from data. So our primary role is to serve the other sciences and improve the inquiry involved with it. So up here we have a traditional definition of what the field is about. Our discipline is about the development of tools for designing studies, both experimental and observational studies, and also analysing the data that comes from it. And it's extremely interesting for each of the talks that came earlier today, each of them used the word data in their description. And the frontiers of those fields are the frontiers in which data is collected and analysed. And so statistics is a collaborator with each of those sciences. The other thing that's really true is that our field is rapidly changing, and the change itself is in response to two things. One is the computer revolution, which has been going on for the last 50 years, in which the improvement of the power of computation has made possible things that were not possible in the past. And the other thing going on is the automatic collection of data on scales and of types that we did not have before. And because data is a raw material of the statistical sciences have changed dramatically in response to it. Our goal of the statistics department at UCLA is primary research into statistical methods, in particular in response to the data revolution that we're going through. The other component, as you'll see from the many applications I'll describe today, is we're fundamentally a collaborative science. We work with the other sciences in improving the overall scientific enterprise. And one of our other goals is also just to coordinate teaching and research in statistics and probability throughout the college and the university as a whole. And we do this through high quality training of undergrads, through a very vibrant graduate program, and I hope many of you will be able to experience this firsthand in the coming years, and also outreach to the high schools and the pre-college schools in the Californian system. So here's some basic facts about the department. We're relatively small with 15 total ladder faculty, tenure track faculty there, and a number of those, 5, are split with other departments. That means they're half in our department and half in a different one. And this just reflects the collaborative nature of our department overall. We also have 10 lecturers, and their primary focus of their work outside the classroom is to research in statistical education, just to improve the overall quality of the delivery of the classes. We also serve a large number of students at UCLA. We have 280 majors, 151 minors, and a number of people in the pipeline getting there. At the graduate level, we have a master's program with currently about 40 students in it, 55 PhD students, and 50 students in a new Master of Applied Statistics program. In total, we have 158 graduate students right now within the department. And we also do a lot of service, not only at the undergraduate level, but at the graduate level. Other students in the physical sciences and throughout the university as a whole take our classes. We're the department on campus that delivers the data science classes and also most of the machine learning classes. And so there's enormous interest in the classes that we provide. What I'd like to do now is focus for the rest of the time on the research of the department overall. I'll then talk about an area of particular interest to me and end off with a couple more examples by other groups within the department. So firstly, the research areas. One is environmental statistics, and you've seen many examples of that today. And the idea there is that we collaborate with environmental sciences to try to improve the overall quality of the work involved and increase the overall quantity of it as well. So we have a number of people here interested in spatial temporal modelling, certainly representation of stochastic processes for those purposes. The second large group is computer vision or computer cognition, and this is a group that works at building the basic models we see every day through Google and Facebook in terms of artificial intelligence and deep learning processes. So in essence, what they do from a statistical standpoint is various forms of pattern recognition. The third group here is computational biology and bioinformatics. The biological sciences, human genetics, and the other schools of medicine are producing enormous amounts of data and have been doing for a fairly long period of time. And so there's a subfield of statisticians who work entirely in the area of trying to make sense of that data and push those fields forward. The area is one broadly defined as social statistics, and that's the area that I'm personally most involved in. And this is to do with understanding the structure of social systems, in particular in the social sciences. So I'll have much more to say about that. We have a number of faculty here, including Aaron Hartman, Chad Hazard, and Tao Gao, and each of these is split. These first two with political science, and Tao Gao with the communications department, and I'll have an example of that work later on. There's also the Centre for Teaching of Statistics, which I mentioned earlier, and they're mainly involved in improving the quality of teaching. One thing they've done is developed a high school level class in data science that is available to many high school students in the California state, and it gets them started on data science before their college level classes. The last group here is one of the most cutting edge groups, and it's a group of statisticians who work on complex systems and very large scale data systems. Most of these do various forms of machine learning, and many of their PhDs are not in statistics, which I think reflects how rapidly the field is changing. Arash Amini's PhD is in applied math, and he does a lot of mathematical statistical work to do with studying machine learning algorithms and network processes. Alison Fletcher, her PhD is in electrical engineering, and she works in the neurosciences. So most of her work is in modelling complex systems from direct neural measurements. Guido Montefar is a recent hire. He's split with math, and he is a mathematician, and his work is trying to understand the theory behind both artificial intelligence models and machine learning models. The structure of why those models work so well in practice is not well known, and so it's a very important area of scientific work. All right, now I'm going to focus on work that I do for a while, which I think is very interesting and also talks about where the field is going overall. So I'm going to focus on network processes, and I'll start from the core ideas here and then work into some more technical notes. So we have here, as most of you know, this is a little stylized cartoon network process, and from graph theory, a network in its simple form is comprised of nodes and lines, which are ties that in fact connect those nodes. So a central component of network processes is the idea of a relational system. We have a set of units of interest here represented by the nodes, and the primary scientific focus is on the structure of the ties that connect those nodes. So networks are very commonly used to represent relational systems. And this is an important component of it. So it's the relations that are of interest rather than just the structure of the nodes themselves. And because of because this notion of relations occurs through so many different sciences, the study of networks is multidisciplinary, not just people in statistics, but through all these other sciences. And so there's an enormous array of possible terminologies used. Nodes are often called vertices, or in some subfields, actors or entities, or some components of them. So it's important when you're studying networks to recognize the different components involved. And probably the most important thing I'll say about it now as we get into it is because networks are such a primal component, the objectives for which they've used, the scientific objectives, also vary greatly. And keeping those objectives in mind is really important when we look at how networks are used and what their value is. And the last one is just a multitude of frameworks for thinking about network processes. Some of them are purely stochastic, some of them are purely deterministic, and so on. They're also extremely used in the social sciences because the subject matter of social sciences is really the structure of social relations. So a very convenient mathematical representation of that. All right. And the last thing is that network representations can be helpful in very many settings. We've seen them in the talks earlier on. We had components of representing molecules. We could look at them in terms of representing star structure, other components like that in the environmental sciences also. I'm going to focus on those social science applications here. But firstly, I want to take a step back and think about something very traditional in statistics, which is survey sampling and how network processes can be involved in that. So first, let's go through a stylized description of how survey sampling works. We have an underlying population of interest, a set of units or nodes, and we might have some characteristics of those we're interested in. I'll just represent it by mu here. And in it we have a sampling frame, and that's just a set of possible nodes we can actually get access to. And I'll just assume for now this is the full population. And then we have an outcome variable, just some outcome measured on each of the nodes or the units here. So the idea here is we have an image much like this, the simplest example where the units are actual people and they exist out there somewhere in space. And the idea here is what we want to do is go through and describe that from an overall general view. Now the idea is what we'll do is go out and get a sampling design. It's presumed the population is sufficiently large or sufficiently difficult to directly observe everybody, but we only have the resources to look at a subsample. And we could do that in a bunch of different ways. A simple random sampling, sample them all with the same chance, or we could have some stratified sample where we would stratify in some measured covariate on the individuals and over or under sample those. So that's very commonly done. We can even do sampling on the outcome variable as well. But the core idea is we set up an underlying stochastic process of choosing them, and we know that process. We then choose the units from that design and then collect data on them. And we have the sampled units. So you can see in the green, I put the green ones about the subset of them, of those who have been sampled. It looks like it's about 10% of this idealization. So that's the idea. So once we have that, we then have to solve the last step, the analysis step. How do we take these folks and infer or estimate the population characteristic mu based on that? Well, this is pretty much a solved problem, or at least we have pretty good answers to. So suppose mu here, we'll define it to be the population mean, so we can just write that as an average over y, which is a characteristic of interest here. So that is what we're interested in. And the fundamental problem, we don't observe all n of these, we only observe a subset of them. But that's not too much of a problem. We can solve it in the following way. We can let SI be an indicator of whether a unit is observed or not. And we observe all of S. We observe for each unit whether it's observed or not. And then we compute from the sampling design the probability that any given unit in our population was observed. And we'll just use pi I to represent that. So this is known for the designs. For example, for simple random sample where we sample small n of them, then the probability of each one being sampled is a small n on big N. And so this is directly computed from the design. And then we can go ahead and use a simple estimator based on that. We want to estimate mu, and we could use a so-called Hayek estimator, which is in essence just inverse probability weighting. We take each of the observed values and we weight it inversely proportional to the probability of being sampled, and we get a normalizing constant here which estimates the population size n, and we take this ratio as an estimate of this average here. And this can be statistically quantified and the properties of it worked out. So this seems like a reasonably straightforward path. And in fact, almost all sample surveys use this basic idea or some minor variant of it. Polling surveys, political polls, everything like that. But let's suppose we have the following problem, which makes that other design very difficult. Suppose we're interested in, say, the proportion of sub-Saharan migrants who are in the country of Morocco and what proportion of them have children. Now, the difficulty with this is that we don't know who these migrants are because we don't have a sampling frame to identify them, so we can't randomly sample them. They're hidden or quite difficult to observe. And we go through some other examples here, and for each of them we see it's very difficult to set up a conventional sampling frame. The number of unregulated workers in New York city, the number of intravenous drug users in Kampala, in Uganda, the proportion of sex workers in rural China who are ethnic minorities, and semi-rural people in the United States at high risk for opioid addiction. And I've worked on each of these problems to answer these fundamental scientific questions and also questions of public health or demography. So the issue with each of these is that we don't have a sampling frame for them, so this method doesn't work. Well, what can we do? We can have a different perspective, and the perspective here is we suppose that the population is joined by an informal social network of relationships amongst the people involved. And then the idea is we have access to some members of these. We can start by going to areas where they congregate, or we know a certain member of them. So suppose these are both true. Well, here's an image now which is a little different than the population we had before. We have the same people, but now we recognise that there's social relationships amongst these folks. So this person here has a social relationship, say they're a friend, or they collaborate, or they exchange email with them, with this person here. So these people have a connection with each other. And this person here has a connection with this person here, 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 and here. So this person has 5 different connections. Well, this person here only has 2. So the idea here is that we have additional information, beyond information about each person, about the relationships that people have, and that we want to exploit this to try to improve the quality of these designs, and hence the analysis. So the idea here is the following. Begin with an initial set, which we refer to as the seeds of people in the population of interest, and then extend the sample by having the researchers sampling those tied to those already in the sample. And this is referred to as link tracing, in the sense that the lines here represent links between people. So in this stylized way, say we started with this person as a seed, what we would do is trace out over the links. This person has 1, 2, 3, 4 links, and we trace out over 3 of those 4 and then find these people. So for example, we would ask this person, who have you sent email to in the last week? We could then randomly sample from the subset of people they've coordinated with, and then go out and interview those based on that information. So the key thing is here, we didn't know before we started this process that these people existed. We've used knowledge gained from this person here in the process. So this last step is the key notion. What we're required as researchers to know before we start the study is very different than what we can find out as we begin the study process. And then we repeat that going through again. We recruit these people, and then we go through and recruit people from those people. We go out, not necessarily all, but we go out and recruit additional people. And this is referred to as a second wave of the process. The first recruit was the first wave, now we go out and do a second wave. And so by this way, we're able now to collect a much broader sample from the population of interest. Okay, so this is referred to as an adaptive network sampling design. It's a network design clearly, and it's adaptive in the sense it's adapting to what we learn about this particular social network through the sampling process. So here's just a few more stylized representations of these. One is to think about this as a sampling design. We could go through and say, look at this cartoon network here, which if this was the full network of a firm, we could go through and start with 2 sets of seeds, sample out based on the people they've had collaborations with, and they would go out and interview these, and then go out the second wave from those, interview the next people, and then continue on till we sample the large number, or potentially everybody in the network as a whole. So the idea with an egocentric design, we would start with just the people sampled here. It's centric on these egos, and an adaptive design would go further out and recruit the various recruits. Now, a separate version of this is so-called missing data, not where we do it by design, but we don't observe everybody. So imagine these 2 people, we tried to sample everybody, but these 2 people didn't come in on the day because they were sick. So as a result, we don't get the ties, outgoing ties from these individuals here. So their ties are missing. And if we didn't take that into account, we would see the network like this, would act as if there were no ties here, when in actual fact there are ties and people involved. And so we've now got missing data in our network, and our sample is reduced in this way. And the last one I'll briefly say is there's a boundary specification problem where there are people on the outside of the network who influence the network but aren't members of it. So in my example here, these three question marks would be contractors who aren't part of the company itself, but they bridge social ties between people who are. So even though they're not part of the company, they have direct influence on what we actually see. So that's a third kind of partially observed network process. So I'll focus on these, and we'll now work through the properties of it. So this seems like a great idea, but we then have these concerns. One's a so-called seed dependence. You know, the final sample depends on who we sampled to start with. In particular, those people might not be representative of the population as a whole. So our sample is going to depend on who we start with. The second thing is confidentiality. Some populations prefer to stay hidden. We don't see who they are. So that's an important component as well. They don't want to be disclosed. And so we have an issue with that. They won't tell us the information of who they're tied to because they're giving up private information of the people they're socially connected to. So this is a major concern. And the last one, and it's sort of the elephant in the room, that this is a great way to collect data, but it makes it very, very difficult to analyse the data. We had a very simple way of doing it in conventional, non-adaptive designs, but for these designs it's much, much harder. So this is going to be a big challenge. All right, so the strengths of it are it exploits information in the network, which is very good. We can use the network to improve the designs. It increases the range of possible designs. We can be very inventive and so on. So it's a very efficient way to collect data, but these issues I've just mentioned make it very difficult to actually analyse it, which is a problem overall. So I want to talk about a particular version of adaptive sampling that's in very, very common use around the world, and I've spent a fair bit of time looking at this design, and it's a variant of the above, where in our case we require the respondents themselves to choose from among their social circle rather than the researcher chooses. So the difference here is in the first design, the researcher, i.e. us, would randomly sample the people they were going to sample at the next wave. Here we don't do that. We ask the respondents to identify their own social partners and invite their social partners to be involved in the survey. And we do this with a small financial incentive for them. So we don't invade the privacy of the contacts of the respondents because the respondents themselves invite them and they choose to come in and be involved. So this is clearly a very good way to get around the privacy issues. Here, and it's referred to as respondent-driven in the sense I've just described. Link tracing, we don't do any link tracing now, it's done by the respondents, but of course this creates enormous difficulties, as you could imagine, and I'll expand a little bit about this. But before I go through and talk about the technical issues with it, this is extremely used by the Centers for Disease Control, World Health Organization, public health organisations throughout the world, and demographic surveys throughout the actual world. And the reason is it's logistically simple to do. It's probably the main purpose, and of course the populations are focusing on it tend to be hidden and very difficult to sample by other means. So here's a simple example of this, stylized. This is, say, the migrants in Morocco, and this would be the red ones would have children and the blue don't, and they're connected by social ties. Would start with a set of seeds, some of whom have children and most of whom don't. We'll sample out one wave. Some of them have children, and it's more likely for those who start with children to have children here, and then slowly cycle out through the second wave, third wave, and so on through the process. So in the end we get all of the coloured waves, but we're missing a large proportion of the population because they're not directly connected to the social network, and in addition we stop for logistic reasons after a degree of sampling. And so we can go through this process. The last thing I'll define is a degree of a node is defined to be the number of ties, that is the number of social links that a tie has. It's a measure of how central and connected they are to the network overall. So here's an example of that process. I've started off with the nodes on top. These were the 4 or 5 seed nodes, and as you go down the page, these are successive waves. So this is wave 1, these folks down here which they're connected to. This is wave 2, and so on. And what happens here is very common. This is from real data from El Salvador, where what happened is after a while these people don't nominate anyone else, they stop, and other ones go on. So it has this graph tree structure, sometimes very tenuously tied. And so some seeds produce lots of data sample and other ones are quite short. So this is very typical of the data we actually see, and it gives us a sense of what is going on. All right, so how can we change our estimation method? This is what we were doing before. We were sampling with pi, but the key idea here is that pi, the probability of an individual sample, isn't known now because we don't know the sampling design, because we don't know the network, so we don't know how to get through the process. So we go through this here. And so one idea brought forward was to, in essence, replace pi with the degree of the node. And the motivation for this is to model the sampling process as a Markov chain over the graph of the social network. And when the Markov chain hits equilibrium, the overall marginal probabilities of selection are equal to the sequential probabilities of selection, which are proportional to the degree of the node. And hence we can use di in place of pi, because di is proportional to pi. So that gives us an estimator here, inverse weighted estimator, which is referred to as a Volt's heckathon. And so what we can do is then check to see how this estimator does. And that's a pretty easy process to go through. I won't spell out the details here, but what we do is we simulate social networks with given structure, which we can do using stochastic models, which I'll talk about in a little bit. And then we can generate networks with known structure. And then from those we can simulate responder-driven sample over those and see how well it does in populations where it's known. So for example here, we could start with a population of 1,000 people, and we have 20% of the people have the characteristics of interest, then generate networks with a mean degree, average number of ties of 7, and various measures of homophily and differential activity, which I'll describe. So homophily is a social process by which ties, nodes are more likely to be tied to other nodes which are similar to them in observed characteristics. So I gave an example earlier about migrants who have children are more likely to have social ties with other migrants who have children compared to migrants who don't. So homophily is a fundamental empirical property of social networks. So we want to know to take that into account. Differential activity is basically just the notion that those who have the trait of interest here represented by just a general term infected, might have different overall numbers of ties, might be more active in the social network than those without. So we'd like to take these two things into account. So we generate networks of 1,000. We then draw samples from them, starting with 10 seeds. We make those samples representative, and then each of those can recruit up to 2 people through this process of giving out coupons to recruit them. And then we'll see how things work. So here's some simple results, and I'll describe some of these. What we have here are box plots, measures of the statistical variation. And I'll start with the first one here. When we sampled 50% of the population, which is quite large, half of the 1,000 people, what we did is then compute the Volt's heckathon estimator and looked at the proportion estimated compared to the truth, which is on the vertical axis here at 20%. So this is basically saying this box plot is centered upon the average estimator, well, actually the median estimator here, and this is a 25th percentile and this is a 75th percentile of the group. So as we see, the box here is centered pretty much on the true value 0.2. So this estimator is doing very well. It appears to be unbiased, and the variation looks like it's about 1 or 2 percentage points, so it's very low. And this also is true for in other cases where the sampling fraction goes up. So this method does very well when there's no differential activity between the groups. But when we add differential activity, in particular where the infected are more active, have more social ties than the uninfected, then these box plots quickly drop from this line and become much lower. So the estimates are dramatically lower than the actual true values. So the estimator is very bad. And if you think about it a little bit, the intuition's pretty clear. What's going on here is that if the infected are more active, when we do the inverse probably weighted method, we're overcompensating, and so we get an underestimate of the proportion overall. And this is induced in the case where the population sample is large, because we're basically sampling all of the very active people earlier. We also note that if there's homophily, the opposite things happen. The bias of these box plots increases, goes up. So this estimator is not going to work very well in the real world, because we'd expect both of those things to occur. So what we're going to do is a better approach, which is to bring in network models here. So what we're going to do is try to come up with network models that represent the primary properties of the social network we're interested in. And they're the overall activity level, the degree, then the sampling fraction, and then to have the homophily effect and seed selection. And we do this through a super population model for the network process, and use that to assist in design-based inference. So the core idea here is we had a model for the network, or we had a given network Y. We could compute this by just simulating sampling, responder-driven sampling, over that network structure, and then average out over the possible network forms. So, but to do that, we'd need a model for the underlying network Y, given what we've observed. We need a probabilistic model for that process, and then for each given network from that process, we could compute our pi I here, average over them, and get an estimate of the sampling proportion here. But we need a model for the underlying process for that to actually work. So let's talk a little about stochastic models. So the idea here is to formally let Yij be an indicator where there's a relationship, a social tie between actor I and actor J. Then we can think about this capital Y as being just the matrix, this binary matrix here of the relationships. And that is, of course, just an actual graphs we've been looking at. The graphs are reconstructed from that. And we could also construct networks. If you had additional covariates, we could include those covariates and think about both observing the relational ties and the covariates involved. And our basic problem then is to write down a stochastic model for these. So I'll just briefly describe these. We'd want a model which has the mutuality of ties and the homophily effect, and potentially also transitivity of ties. So in essence, it represents a whole bunch of different structures that would be of interest here. And we'll do this through an exponential family class of models here. So I'll just write them down. The idea here is what we want to do is come up with a class of probability mass functions for the graph, and we'll choose the probability mass functions which maximize the entropy over probability mass functions of it, subject to constraints on the probabilistic mechanism, in particular the constraint that the expectation of graph statistics, these are things like the average degree or the degree of mutuality of ties, counts of those things, that the expectation of those is equal to some pre-specified level mu, which are the parameters of the model here. So we choose as a class those which maximize the entropy subject to constraints, that certain characteristics of the graph are fixed, that we fix those characteristics. And this quite famously leads to so-called exponential family models for networks here, which can be re-expressed in terms of the graph statistics over Y. So the probability of a graph y is equal to these graph statistics here, and this is just a normalizing constant. And they also satisfy these constraints, the mean constraints of interest. So this gives us a very broad class by the particular choices of G, the Gs that we actually think are important for the model here. So we can go through and give many characteristics of these. I won't dwell on this one here and go through the process, but I'll give a simple example. If we have the so-called Bernoulli graphs, or the famous Euros-Régnier models, where all the ties are equally likely and independent of each other, then you can show that the probability mass function is equal to e to this, where this is just a sum over y, which is the total number of ties. So the probability mass function is just proportional in exponent to the number of ties in the network process. So this is a nice simple model for what is going on. And we can represent things like degree heterogeneity through putting degree statistics here, choosing the graph statistics to be the degrees of each of the actual nodes. This is easy to do. Now, to do inference for these models, it's actually quite hard, and I won't dwell on it, but we use this using, we can do this using likelihood framework here. This is the log likelihood for the model. And to compute this, we have to compute the normalizing constant, which is hard. And we do this using Markov chain Monte Carlo methods, which I won't go into, but are very popular in the field. It's a computer simulation. So the idea now is, if we had a model of this form, can we go back and use that model to get better estimates of the inclusion probabilities here? And we can, in essence. We go through and we take our sample, we fit the model to that sample, we estimate the characteristics of the model, then we can simulate graphs with those characteristics and then sample over them, as I've described before. And so based on this, we can go through and estimate this process. Those new pies, which are given here, the pies we get from that process I've described earlier, these model-assisted pies, are then plugged into the same formula here, referred to as pi MA, and this gets us through the process. So I won't dwell on this so much. You can compute standard errors using a parametric bootstrap, but I won't dwell on that. And so let's go back to the simulation study to see how well it does compared to the previous estimators being used. And here they all are in the case where there's no homophily, no differential activity, and they all work well. The model assisted's down here, it's the green, and this is the Volts heckathon, which is the one that's been used a lot. And this, just for reference, is a sample mean. So the sample mean's an obvious one to use, but it's probably going to be pretty bad. Here, it's not as bad as anyone else. In fact, it's optimal here. Now, if we go through and have homophily, what we see is the Volts heckathon estimates lower, and the model assisted, because it has homophily in the stochastic model, can adjust for it and is bang on target. The target here is here. And if we go through and have all infected seeds, so in this case we start off with people who are all infected, so we're going to get a biased sample. The method can adjust for the biased sample because we can simulate biased samples directly from the network model. We can generate networks and then do biased sampling over them. So it can automatically adjust for this as well, where the other methods are biased high or biased low. All right, so that is sort of the end of that method, and this particular model-assisted method is very generally used in the field. Our group's also written software which we provide open source and free of charge for people because they don't need to know about Markov chain Monte Carlo to compute survey sample estimates, but now they can. So that's one thing to do. So in the rest of my time, what I'd like to do is talk about other work that's being done. First, I'll start with some work that I'm doing in collaboration with folks in Mexico. And one of my co-workers is Martin Felix Medina. So he and I have been working together on a generalization of this scheme. And the idea is how to choose the seeds, which is very difficult to do. So Martin had the bright idea of going through and starting out with sites or venues where people might congregate, and a natural place for many of these are bars or community centres. Start off by sampling those, sample these venues, and then trace out of these to the broader population. So here's the idea. If you think about each of these boxes being a bar or a clinic or some place where people meet, then what we do is we randomly sample these, and then from those essentially do link tracing out, either respondent-driven sampling or adaptive network sampling from this process. And sometimes we sample people in other venues, and then we identify that venue again for wave tracing. But more importantly, we often identify people who don't go to these venues, but are tied to people who are in these venues, because we don't believe that, say, all people go to bars. So the people who don't go to bars might know people who do, and so what we can do is sample those, and then we get seeds, and then can do additional sampling out there. So Martin has worked on this before, and he and I are now working on generalisations of this scheme. The other one, which is very interesting, is an alternate form called time-location sampling. And in this idea is, instead of sampling spatial locations, you also sample time as well. So I'll give an example here of another thing that I've been working on in Mexico, and this is the so-called EMIF. And the EMIF is a survey of migration of at the northern border of Mexico, and it's run by I'm not going to pronounce this correctly, the College of the Northern Frontier, COLEF, and they've been running this for 30 years or 25 years. And what they do is, I'll just go to the next figure here, what they do is they randomly sample venues in cities on the northern border here, with the objective of trying to look at migration flows into the United States and migration flows outside. And they're extremely difficult to accurately measure. So what they do is they randomly sample venues, and then they randomly sample a time during the 24-hour clock, and they'll go and sample people at those venues during those times. And the venues will be things like bus stations, airports, train stations, and things like that. So they're doing this on a very, very large scale. And they're sampling 14,000, 20,000 people per year, both coming into to Mexico and leaving Mexico. And this is, I've studied a lot of time-location surveys, and this is by far the best one in the world. It's extraordinarily well executed. The analysis of it's very challenging, but they've done a very good job of doing similar computations to what I've just shown to compute inclusion probabilities by sort of very complex design. So this is very interesting. So if you're interested in surveys, this is a very good one to start with, because of the overall quality of it, and also just because of the really interesting results it has as well. And they do a similar thing on the southern border and so on. All right, so I just finished this area about this hard-to-reach population sampling. Network estimators are very useful here, but they require the specification of this stochastic model, which is enormous amount of additional computation, but it leads to great flexibility in their estimates and more accurate measures of uncertainty from it, because they more accurately represent the true social processes. There are ways of trying to improve these, and one of these is privatised network sampling. And in this idea, you don't collect information on the alters, but you would only collect, say, a 4-digit number, so the last 4 digits of their telephone number, to identify them. Now, 4 digits is accurate enough to have almost perfect individual identification. If you think about it, it's 1 chance in 10,000 of 2 people matching. So as a result, it's effectively unique, but gives up no private information on the person. So we've been exploring these designs to have adaptive sampling at the same time as it's privatised. Go through this process here. Now, I wanted to talk my last few minutes just about some other work done within the department in collaboration and at UCLA. And this is the collaboration between statistics and the Department of Communications, which is in the social sciences division. And this is to do with collecting data on the media. So what they've done is collect video and audio of news broadcasts starting from 2005. So they literally have old VHS tapes of all the news broadcasts, which they've painstakingly digitised to have both audio and visual. And then they've used statistical learning methods or machine learning methods to translate those from audio to text. So they're doing audio translation, all with algorithms, not by hand. And so they have translated all of these into text, and the video images are also processed as well. So the key notion I want to communicate is we don't think about news and TV as data. But what in essence I've done is I've converted these to data, text data and other forms, video data involved. And I wanted to show the sort of things that they do with it, just a couple of simple examples. And in the United States, the media have different ways of presenting the news. And so I've chosen 3 different groups here: Fox News, MSNBC News, and CNN, which are 3 networks. And I've put them in a spatial array here. So what they did is they recorded everything that these guys were broadcasting, audio, visual, and then translated that to see the proportion of time that they discussed certain topics. And if you can't see this really well, but I'll show you a little bit closer, each of these circles represent a given topic discussed about, in this case, it was about healthcare. What were the important ideas here? So the circle represents how often it's discussed. The title, which is a little hard to read, the next one will be easier, is in the centre. And more importantly, the location gives you the relative composition of how often that topic is discussed. So if this circle is closer to MSNBC, it's doing most of this discussion. If it's closer to Fox, it's doing this discussion. So this very simple visualization gives us a way to understand a very complex topic, which is the relative coverage of different topics by different networks through many thousands of hours of audio-visual representation. So I'll give you a sense of this just by showing this guy here. So here's an example where we've got the 3 started. So I'll start this going in a minute, and you can see what's going on, the various topics discussed by Fox News. They've put some figures here on some folks. This is Ted Cruz, I think. I can't see. Make these guys out with my glasses on. Here we go. So I'm starting it moving forward, and as you can see, as it goes forward, you see various topics involved. This idea of clause over here. These guys here, MSNBC is talking about Beck and angles and all these various components, and repeal. They're very important. And then over time, as they're analysing the data over time, you can see a time step going on here of days. You can see how these debates evolve, how certain topics are covered for certain days and they're not being covered. And some topics that start out over here and then slowly are dragged away into these different areas. Some become more important, some fade out, some people become more important. CNN over here, Newt Gingrich, moving back to the centre here, and these various components evolve. Now Newt going back up to MSNBC. So, and then you can see how this process evolves over time. So the point here is really to indicate how we start off with a very complex data set, which is very difficult to quantify and represent, and simple statistical summaries of it can give you a very good sense of what is going on, and a very good sense about the relative composition of discussion. Right, I'll have one other example I'll show here of this work, which is a similar notion. This one is text modelling, slightly more sophisticated, during a crisis. And this is actually during, there was a shooting in Santa Monica College, which those of us from UCLA will know very well, because it's about 5 miles away from where we work and many of us live. And but other people from Mexico might not know it very well. But what happened is there was a shooting in the college a period of time. And so what was done was follow the news media starting from when the incident occurred, then use the automatic statistical algorithms to extract out the topics. But in this case, instead of using words, they use so-called topic modelling, statistical models, to identify the various topics being discussed by the news media at any given point in time. So this is really looking at the trajectory, if you will, of discussion of a shooting from the moment it occurred to the end of it, of which of these events ask about two weeks. So let me start this process here, working through it. So firstly, the shooting occurred, just moving forward, yes. the shooting occurred, and you can see down here this various thing, the word shooting gunman suspect, this is topic modelling down here. Then over time, a couple of days, they turned up this extra person and wanted to discuss the shooter's name, and then it moved on to these broader issues that weren't sustained by these about gun control and these broader debates about where it's at. Note, as the overall discussion, it starts off extremely high and just sinks down in terms of magnitude, but also the topic composition changes over time throughout these events until it basically peters out. So that's another example of, in essence, how statistical methods can be applied in areas which, when you first think about it, seem non-statistical, but also very difficult to get any quantitative or scientific angle on. And these work forward in that way. All right, so go forward here. Oops, great. So that, in essence, I'll draw it to an end here. The last thing I'll really say is that I think the field of statistics is in the midst of and will continue to be in a golden age. If you're a scientist but can't decide what your subject matter will be, being a statistician means you can work in a number of different fields and find out this amazing scientific facts and understand deep scientific ideas. It's a great topic if you want to understand science very broadly and can't choose amongst the various scientific fields. So if you're thinking about graduate school or postgraduate work, please come to talk to me after. I'll be very happy to talk with you about the field, but also the opportunities at UCLA. We're always looking for great people, and I'm sure you're out there. Thank you very much.
Thank you very much, Mark. A wonderful presentation. So why don't we give a chance to the audience to ask questions. ¿Alguien tiene alguna pregunta para el profesor Hancock? Sí.
Esto es la ciencia de las estadísticas. ¿Algún día podrá aplicarse para el análisis de las redes criminales, de la corrupción? Es decir,
no quiere preguntar otra vez.
Toda esta herramienta, toda esta ciencia.
Un momento.
Toda esta ciencia nos podrá acercar algún día al análisis y a la identificación de redes criminales de la corrupción, donde entran políticos, entran financieros, toda una gama de criminalidad muy potente y operan en redes. Ese es el problema. Las redes son subterráneas, no hay información, no hay contacto. Es muy difícil hacer el modelo. Pero algún día podríamos llegar a hacer un modelo. Lo que sí hay delatores. En la actualidad se está destilando delatores que nos llevan a ciertos nodos de la criminalidad, pero todavía está en pañales para mi gusto. ¿Ustedes lo han vislumbrado?
Thank you very much for the question. In fact, this is precisely where the areas I was talking about are most applicable. Because if you think in those contexts, the networks are extremely important for the illicit behaviour, and they're hidden in a very explicit way. More importantly, we know very little about them, that we only partially observe them in very small pieces. And so it's very important to bring as sophisticated methods as we can for the analysis of them. In fact, this is of great interest in the field. I'll just quote one example. It's by Michael Swenberg and myself in 2011, where we analysed at that time the Bali terrorist network. There's a terrorist event within Bali, and we worked back from the network of ties between the various terrorists involved to identify who the ringleaders were. At that point, as an illustration, we knew before we started it who they were. It was to show that the methods actually worked. But there's an enormous interest in the science of doing this. I would say it's also important to say that these are very complex international societal problems, and clearly these methods would be very helpful in identifying those networks and bringing appropriate police behaviour to bear. But the underlying driving forces are social forces. They're the ones that need to be changed before the problem itself can be resolved.
¿Alguien más tiene alguna pregunta?
Okay. So I understood that the network sampling technique was used to find hidden participants, meaning that they would otherwise not be otherwise not participate. But I'm thinking that this method could also be used to find hidden participants, meaning that they don't know that they have the disease. For example, here in Mexico, to estimate the proportion of people with diabetes, which is one of the top diseases, they have to do a national survey, which is very costly. But maybe actually there is a paper stating that maybe diabetes and non-communicable diseases are also a little communicable, meaning that they can, in a way, transmit from one people to another. So yeah, maybe this technique of network sampling could be used to find people that don't know have a disease.
That's a very good comment. In fact, it is. The original examples of this are actually for HIV, where the idea is you would interview the person, ask them demographic questions, but also give them a blood test. So they didn't know they were HIV positive, unless they, they obviously didn't have. They had the option of not looking at those results, but they could find out it. The other thing, diabetes is a very good example. In the United States, there's a study actually run out of UCLA that exactly does this, uses a link tracing design to identify people at high risk for diabetes. And they don't think diabetes is communicated, but it's in a direct sense, in a contagion sense. But it's certainly true that people who are at high risk for diabetes are more likely to have social ties to people who are. And they were using this process to help, in essence. They would then focus social services on people who were at risk. So they were much more efficient in the delivery of social services, both in terms of finding out people who had hidden diabetes, as you say, but also making sure you weren't giving it to people who didn't have it, because most of the other methods are very broad-based. They would say everyone who went to a clinic or everyone who lived in a certain area, as distinct from a much more targeted version, which these ideas imply.
¿Alguien más? Allá atrás.
Hi, I am in the area of bioethics, and I wonder what, from your experience, what are the risks of using these models and collecting data, like medical data, like this big data that we don't really know who is collecting this. They are collecting it from our applications in our cell phones. And the purpose of these companies or even governments or researchers, and how can we protect ourselves? You talk about privacy, and I don't know if you did talk about consent, but there is a tacit consent in applications or internet. So can you tell us a little bit more about it? Thank you.
And it's also an extremely good question. There's two questions there. I'll answer the first one. In scientific studies, consent is an essential part of it. Any of these studies go through the same institutional review boards that standard clinical trials go through. So they have to ensure they have proper data management, confidentiality protocols, data storage, consent mechanisms, implicit consent mechanisms, privacy of others. It's extremely important they go through the same protocols. I would emphasise, though, the points you make are very important ones. If those protocols weren't in place, there's a lot of room here for abuse. Now, to the second question, which is more broadly based, non-scientific research, but areas in which commercial companies are collecting data. And this, of course, is a very broad topic. And there are many, many views on it, and many of those have value to them. The world is a rapidly changing place, and ideas that worked very well 20 years ago are not going to work very well into the future. I have a personal belief on this, which is I think we should focus on the notion of personal data property. And this is the idea, is we should say, if we're giving up information to companies, the thing they'll listen most to is the monetization of that. So if we give our geographic position up to a company, in some direct economic sense, they have to pay us for that process. Now, at the moment, the agreement is implicit. We use Google, for example, just to mention one, and they provide fantastic software resources, which I myself use and I think are extremely good. And implicitly, they take the information and resell it as a process of their business. My belief is that we should make that much more explicit and definite, to set up mechanisms to recognise that we're selling something to these companies, and we should be willing to negotiate a price, and then everyone can decide themselves what they're doing. My description is very simplistic, but that core economic notion, I think, is key to solving this problem.
¿Alguna otra pregunta? I'm curious about one thing, Mark. So you talked a lot about sampling and basically data collection, and data collection is guided by some characteristic of the population that you're looking for. And I'm wondering if there are interests or studies when you develop one of these surveys or something, if there is some additional things that you can ask that then you can look for correlations and then increase the amount of information that you can get well beyond the original objective.
Yep, that's exactly right. I mean, the advantage of these methods being adaptive and sequential is that you can use any information collected prior to the current wave to update those waves. So that your example is a very good one. If we find some emergent behaviour as you work through the process, we can use that to direct focus and improve subsequent sampling. Then the advantage of the methods I've described here, which is a model-based method, is we then need to go back and look at the impact of that changing decision, the decision we've made as we've moved through the survey. And without a model for the network, it's extremely hard. But with a model for the network, you could simulate those behaviours and look at the impact of your choices. It's exactly that power and flexibility why the model-based methods are so useful. They free the surveyor, the researcher up, to make the best choices they can make, and then give them a mechanism later on to rationalise those choices.
Thank you. I think I have another question, if I may. So when one applies data analysis to social problems, I have an intuition, which is probably incorrect, but I'll ask it anyway, that human behavior is very bound, is very constrained, is relatively limited, such that I would imagine that all the solutions are within a relatively narrow range. And my question is, would there be any circumstance where you do a sampling and you get a completely off-the-wall answer that is nonsensical? Or is it always really, as I'm imagining, relatively well within certain limit of expectations? can you get something ridiculous out of a poorly defined, data sampling or data analysis?
Well, these methods are used to collect characteristics of populations, and we can find very extreme things for it. For example, for HIV, we might find that broad subpopulations have no HIV at all in them, and others are actually surprisingly hit. I'll give just one example of that. There was an outbreak of HIV in rural Indiana next to the Kentucky border, in an area of the United States which had never seen anything like this before. And there were a large number, hundreds of people who were infected. And they couldn't work out why. And they did a survey to discover it. So it was an enormously surprising thing. And it only worked out later that it was in fact a side product of the opioid epidemic in the United States. They were doing needle shearing for opioids, and they were once one case of HIV got in there, you had this result of it. Is that the sort of thing you were thinking of, or am I missing, or was there another example of what you were thinking of surprising results?
No, I think that's... creo que estarán de acuerdo que las posibilidades y el uso de la estadística es increíble, viene en muchas formas y creo que es un tema que seguramente, como la matemática aplicada, también va a ser muy importante para los jóvenes. ¿Por qué no me ayudan a agradecer al profesor Hancock por una presentación excelente? Thank you, Mark. Sí, tengo. Y bueno, con esta presentación vamos a terminar nuestro programa, pero quería comentar algunas cosas y inclusive, no sé, tal vez podíamos tomar un par de minutos, si es tal vez interesante para ustedes, regresar y preguntarle a algunos de los ponentes de la mañana si hay algo que les llamó la atención, que tiene que ver con sus pláticas o con las disciplinas o con los departamentos que representamos de UCLA, del área de la bioquímica, del área de la química, la física y la astronomía, las ciencias de la Tierra y del espacio, las ciencias atmosféricas y oceánicas y la estadística, desde luego. ¿Hay alguien que tenga alguna pregunta en general de ello que les interese? Si no tienen una pregunta ahora, los invitamos desde luego a que se comuniquen con nosotros por correo electrónico y con gusto les podríamos tratar de responder cualquier curiosidad que tengan. Bueno, una cosa muy interesante de la Universidad de California en Los Ángeles, desde luego, es el propio nombre de la universidad. Estamos en la ciudad de Los Ángeles. No sé cuántos de ustedes sepan, pero he escuchado que la ciudad de Los Ángeles es la ciudad donde se habla más el idioma castellano, es el segundo lugar después de la Ciudad de México. Habemos más gentes que hablamos castellano o español, o alguna forma de español, algunos hablamos un poquito más Spanglish, que aún en Buenos Aires o en Santiago o Madrid. Los Ángeles es una ciudad que tiene una población hispanoparlante muy, muy alta. Es una ciudad que tiene, desde luego, unas raíces hispano-mexicanas, y es una ciudad donde realmente estimamos la posibilidad de tener más colaboraciones con México. La Universidad de California en Los Ángeles nos vemos como tal vez un foco de una red que tal vez pueda tener una interacción grande entre la ciencia mexicana y la ciencia americana, especialmente en el estado de California. Comentaba cuando daba la presentación que somos una universidad muy interesante en muchos aspectos, pero una de ellos es que tenemos una población de estudiantes muy heterogénea. Tenemos estudiantes realmente de todas las culturas, tenemos estudiantes que tienen su origen de muchos países, cuya primera lengua puede ser muy, muy muy diferente. Muchos de ellos su primera lengua es el español. Y es una ciudad también o una universidad, perdón, un campus que tiene una característica muy interesante. Tenemos un gran número de estudiantes de los que ahora se conocen como Dreamers. Estudiantes cuyos papás emigraron muchas veces ilegalmente a los Estados Unidos y se los llevaron pequeñitos y no tienen la nacionalidad americana y ahora tienen una situación muy, muy difícil porque el gobierno actual es, como lo sabemos, no muy amigable de tener una frontera más abierta y de darle la bienvenida a los inmigrantes como había sido la tradición de la sociedad americana. Y una cosa que es interesante es que me gustó mucho que la Universidad de California, no solo Los Ángeles, pero toda la Universidad de California se solidarizó e inmediatamente les dio apoyo a todos estos chicos, a todos estos estudiantes, apoyo legal y apoyo social, en hacerles saber que son bienvenidos, su talento tiene valor, que los queremos, que son parte de nosotros y que realmente vamos a hacer lo que podamos por asegurar su éxito. Son tal vez 800,000 Dreamers en todos los Estados Unidos. No todos ellos son mexicanos, no todos ellos son latinoamericanos. Hay muchos Dreamers que son de países asiáticos e inclusive de países europeos. O sea que no es un problema nacional, nada más de la comunidad mexicana inmigrante, es un problema realmente muy grande. Y una de las cosas que se vienen a la mente es cómo reaccionamos en la población cuando no tenemos una identificación completa con el gobierno actual, ¿no? Y la verdad es que, como se puede esperar para una sociedad tan complicada, tan grande y tan diversa, no es una sociedad homogénea. Desde luego que hay muchas gentes que apoyan el gobierno actual y hay muchas gentes que lo cuestionamos. Pero lo que sí no hay ninguna duda es que las comunidades científicas son comunidades que tienen los brazos abiertos, que reconocemos la importancia de tener una interacción social e intelectual con todo el mundo y que siempre vamos a tener las puertas abiertas y que esperamos también que siempre nos reciban con las puertas abiertas en otros lados. Podemos... Gracias. Creo que eso siempre ha caracterizado a las sociedades científicas, que es la ciencia lo que nos une, y eso creo que es muy importante, que aunque nuestros gobiernos, ahorita le tocó al gobierno americano, otra vez puede ser otro gobierno de otro país, que no tengamos una identificación con ellos, que de todas maneras creo que los lazos científicos nunca se van a debilitar ni se van a romper. Me parece que eso es muy, muy importante. Entonces, al final de este día, realmente nada más me queda agradecer a nombre de mis colegas y a tanto los que venimos esta vez como los que están en Los Ángeles por la bienvenida que nos han dado. Es una oportunidad realmente increíble para nosotros poder venir a compartir un poco de nuestra ciencia, poder compartir un poco de nuestra visión de la ciencia. Creo que todos mis colegas les comentaron que estamos no solamente en UCLA, pero en todas las universidades americanas, hambrientos de talento, de gente que puede contribuir. Y igualmente sabemos que aquí hay muchas áreas para que nosotros podamos venir y colaborar y contribuir. Así es de que ha sido un día fabuloso. Le estoy muy agradecido al profesor Juaristi por la invitación, por la oportunidad de venir. El Colegio Nacional, claro, es una institución única, es una institución ejemplar en México y es un verdadero orgullo venir aquí y poder charlar con ustedes. Entonces, pues nada más me queda que agradecerles a todos. Muchísimas gracias y ojalá que esto lo volvamos a hacer algún día no muy lejano. Gracias.
y queremos agradecerles a nombre del Colegio Nacional su presencia aquí y pues los esperamos en otro evento lo antes posible. Muchas gracias.